All right, so let's look at this one. So again, we're going to write equations for shear force and bending moment. This is a function of x. Can we write one set of equations that are valid from A to B?
No.
Yeah, the answer is no. You can see I've got a continuous load from A to about 12 feet. So I have a continuous load. I can write a set of equations that are good from, say, 0 to 12. But from 12 to 20, I'd have to write a second set of equations. But we should be able at x equal 12 to check those to see if they match. Let's start with imagining a cut here, which would be at some distance x. Do you want to work the left side or the right side?
We have to find our bending moment and shear.
Yeah, if you go to the left side, you will have to find your bending moment and shear force here. That's not terribly hard to do. If you go this way, though, you're going to get some really kind of odd x minus 20 minus x and 12. You're going to get a lot of odd little things going on there. You could go either way. I would go ahead and get the reactions because that way you can make sure your equations match those things. So from 0 to 12, I'm going to go left. But now when I cut it over here between 12 and 20 and decide whether I want to work the left side or the right side, I think you can see the right side is going to be way less complicated. So I'm going to start off using the left-hand part of the section from 0 to 12, and then I'm going to use the right-hand part of the section from 12 to 20. But either way, I'm going to need my reactions to start with. So I'm going to go ahead and assume that I have a positive shear force at A and a positive bending moment at A. And I'm going to find those things first. I think to do that, I'm going to need my concentrated equivalent here. That's a rectangular load. So it'll be base times height. So base is 12 feet, height is 4 kips per foot, so that's 48 kip force. And it's going to be right in the middle, so half of 12 will be 6 feet from the left edge. So I'm going to find these reactions first, so I'll start by summing moments about A. And of course, I like to use right-hand rules, so I'll do that again. So summing moments about A with my statics equations using right-hand rule, this moment is positive or negative? It is negative. And my concentrated equivalent force is creating what kind of moment about A? Positive or negative? Also negative. So the force is going to be 48 kips. And the distance from A to the centroid, 6 feet. Then I get all the way out here on the end. I've got a 20 kip force. That's also creating negative moment. And it has a moment arm of 20 feet. So from that, I should be able to find that my moment at A is negative. I don't know what that is off the top of my head. Anybody know what that is off the top of their head? 588.
688.
Oh, I was close. So it'll be 688 kip feet. And then we can sum forces in the y direction, and we should be able to find our shear force. So again, I'll assume up is positive. So my shear force is up. My concentrated equivalent force is down. And this 20 kip force out here on the end is also down. So it looks like the shear at A is 68 kips. So I'm going to start at A with a positive shear force and a negative bending moment. So let's come here and look at an x range between 0 and 12. So this set of equations will only be good under from 0 to 12 because that's where this load is continuous between that range. And then I'm going to draw my free body diagram for that section. Remember, I'm doing the left-hand side, so I already know I've got a shear force that's up of 68 kips. And I have a bending moment that looks like this. That's 688 kip feet. And then I have a distributed load The distributed load has a constant intensity. It's 4 kips per foot. I'm cutting it at some distance x. And at the cut, I've got positive shear, positive bending moment. Remember, cutting here and we're looking to the left side. So I'm going to replace my distributed load by an equivalent force at some distance. And I can quickly compute that the force is just, it's rectangle, so it's just base times height. That's just going to be 4x. And the distance from the cut is, it's a rectangle, so it's half. So it'll just be the distance divided by 2. That'll be x over 2. So I've got everything enumerated and laid out. It looks like it's okay to me. You guys see anything? Did I miss anything?
Other than your normal force going out to the end.
Yeah, we're not doing that.
Yeah.
There's no axial force. All right, so now we just make sure it's in equilibrium. So we'll start with summing moments at the cut and making sure it's in equilibrium. So let's see. Starting here, that moment with right-hand rule is positive, so that's moment, m. The force is also creating positive moment. The force is 4x. The distance is x over 2. I get to the end, I've got this 68 kip force. That's creating negative moment. 68 at a distance of x. And then I've got the supplied moment at the end. According to my sign convention, that's a positive moment of 688. So just solve for m. I'll just collect all the terms first. So it looks like I'm going to get negative 2x squared plus 68x minus 688. And those will all those terms will have the units of kips, of kip feet. Can I check that equation?
Yes.
Well, remember, it's only valid from A to here. So the only thing I definitely know is I know the moment at A. We solved for it. It was negative 688. When you put in x equals 0, you see you get negative 688. So that works. Later we'll find another way we can match it up. But right now that's all I've got. We'll just have to hope we've done the best and move on. So let's move on. So now we'll sum forces in the y direction to find our shear. I'm assuming up is positive, so that force is down, so that's negative shear. Negative force, which is minus 4x. And 68 is up. So when I solve for the shear, what do I get? Looks like I get minus 4x plus 68. And that will have units of kips. Now we can do couple checks. So I should write this over here. So we've just checked that the moment when x is equal to 0 should be minus 688. Kind of ran out of room. Sorry about that for the units. And we did check that, so that worked. Now I can check my shear at x equals 0. It should be 68. And my equation when I put in x equals 0, hey, 68. And now I've got this kind of secondary check where I can say, hey, is the derivative of the moment with respect to x equal to shear? And it looks like, hey, that works too. So far, so good. So now we're on to how the shear force and bending moment vary in this section, which will be from x equal 12 to 20. So I'll come and mark that. So this set of equations will be good from x equal 12 to 20. So I'm looking to cut somewhere here. And as advertised, I'm going to do the right-hand side of this one. So let me draw that. So here's the right-hand chunk of the beam, which on the very far edge, I have a 20 kip load. That cut occurs at a distance of x, and then this little piece that's left over is 20 minus x. So as x varies, the remaining portion, or this segment, will be 20 minus that. And then now, I'm going to draw positive shear force and positive bending moment on that surface. And those are the two things I'm going to solve for. So just like before, I'll start by summing moments at the cut. Let's see what I've got here. I've got this internal moment. I'm using right-hand rule for my sign convention for my statics, and that's opposite that. So that'll be a negative moment. And about the cut, this 20 kip force also creates negative moment. So that'll be minus 20. And what's the distance from the cut to 20? 20 minus x. So now I can solve for the moment. The moment, as a function of x, is just minus 20 minus x. And that'll have the units of kip feet. Now some people feel the need to expand that. You can if you like. But that's a valid equation. Do I know anything about the moment from 12 to 20? I don't know what it is interior, but I know what it is at B. What's the moment at B? So the moment at x equal 20 should be 0. And if I put an x equal 20 there, what do I get? 0. So that works. Yeah?
Okay, so for the first moment, we did it from the left side, and this time we're doing it from the...
Yeah, so the first one when we made our cut, we used the left-hand side, so there's positive shear force on that right edge of the moment, of the segment. This time we cut it and we went right, so this is positive shear force and bending moment on the left edge. Remember, positive shear is going to make the thing want to rotate clockwise. See, it's going to try to rotate clockwise. And if you get out your paper and you bend that corner, you should see this thing try to turn into a smiley face. That's why that's positive moment. All right, so what's the shear? Well, we just sum forces in the y direction. And what do we get? Well, I say up is positive, so that's up, so that's a positive force. 20 is down, that's a negative force. That's a pretty easy equation to solve. Looks like shear as a function of x is constant equal to 20. I'm going to have to talk to you about how to know what the shear is right there. But for right now, we can check to see if the derivative of the moment is equal to the shear. And is it? It is. So that's one good thing. Now, how do I know what the shear is at that free end like that?
It's equal to the point load coming down.
Yeah, so let's think about that for a second. What if I don't have much room to draw it? Think about this cut sliding all the way over as close as you can get. So think about this shear force getting closer and closer. Let's say X is almost 20, but not 20. Right? Almost 20, almost 20, almost 20. What's the shear going to be right at that point? It's going to be positive. It's going to be equal to 20. And that's what it is. The equation tells you that it's 20. So just imagine X getting, 19.9999999999999 forever. It's still going to be what? Positive and 20. Or nearly 20. So that's good too. There's one more thing we can check. Both of these equations share 12. This one has an upper limit of 12. This one has a lower limit of 12. I'm going to let you guys do this. I've kind of run out of space. I'll try to squeeze it in right here. So let me go back and call this region 1 and call this one region 2. And I've defined them here. So this would be I and 2. So what is the moment from the first equation at 12 should be the moment from the second equation at 12. So you guys will have to calculate that. If you put 12 in there, that'll give you the left-hand side of this. If you put 12 in there, that'll give you the right-hand side of this. That one I can do. You put 12 in there, you get minus 160. So somebody put in 12 here and see if you also get minus 160. That means the two equations will give... Oh, I see somebody's head bobbing, so that's also true. So there's another way of checking. The only time this would not be true is if exactly at 12 there was an applied moment. And the difference between the two values would be the exact value of the applied moment. What about the shear? Well, the shear from equation 1 at 12 is probably going to be equal to the shear at equation 2 at 12. Well, we know equation 2 is 20, and you come up here and you put in 12, what do you know? You get 20. So there's lots of ways, as you can see, all the green checks we made along the way. There's lots of ways to check your equations to see if they're valid. Now, this could be all wrong if I did what? If I messed up at the very beginning and didn't have my right reactions. So this is all dependent on the fact that you can find reactions in the beam. Okay, that one took only 18 minutes. See, we're getting better and faster. Isn't that good? Yeah. All right.